Okay, so in the last lecture, we introduced gradient descent, and then we introduced how optimization can be used to solve this problem known as regression, which is a subset of machine learning, supervised machine learning. We didn't get to use gradient descent on that problem. So today we're going to actually show how gradient descent can also solve the linear regression model. So recall, so maybe we have a problem, right? So the problem is we are given data The data is just a collection of points. Okay. Where xi is a feature or a measure of that data. And yi is a numerical label for xi. So we make some measurement xi, and that measurement corresponds to some value y, and we're trying to use, so actually I didn't write that down. So we're given this, so we want to use that data to make predictions on unseen data. And we're going to use calculus. Okay, so that's the general problem. Okay. And the model that we're going to choose to solve this problem, as we discussed last lecture, is called linear regression. So we have our x-axis and our y-axis, and suppose that we have data points that look something like that. So our goal, and maybe I shouldn't put that, maybe I should put it up here or something. So this is the collection of data where each of these points has an x and a y. The x is what we measure and the y is what we observe. So our goal is to fit a line that best fits that data, that minimizes the error when the line is compared to the y values, when the line is compared to those points. So last time, if you recall, we were optimizing to find a weight to find the slope that best made the line approximate that data. But in general, for a line, there's a slope and an intercept, right? So today we're going to consider where there's an intercept. Now, because we don't have access to multivariate calculus, we can't optimize for the intercept as well. we can only optimize the weight. Okay. And when I say multivariate calculus, so in Cal 3, or the sequel to this course, you'll learn about taking derivatives of functions that have more than one variable in them. The derivative of that type of function is called a gradient. So when you hear derivative and gradient, it's the same thing, just gradient has more than one variable involved. We only know about derivatives for one variable, so we can't use that. So the best that we're going to be able to do is to guess the intercept and then optimize the slope. So for example, this data here, we can more or less see that this point's somewhere near the y-axis. So we can just kind of choose the y associated with that point, or like a little bit above or below. And then we want, so we'll call the intercept there B. And this line would be equal to W times X plus B. And we want the best W. We're going to use what we know from Cal 1 or calculus to find that best W. And we're going to guess the B. But no, in general, you're also going to use calculus to optimize that. Okay. But sadly, we can't cover that in this course, optimizing both. But I think it's a good exercise to learn how to optimize this one variable. Optimize means find the best, right? So I'm going to introduce some notation here. So for a given W and B, so a slope and an intercept, let y hat be our prediction. So y hat is just supposed to be our approximation to what the points are, how high up they are, right? So in particular, what that means is that y hat is equal to the weight that we're looking at times x plus whatever intercept that we picked. Is that clear? And W is what we're going to move around a bunch of times. We're going to try to find the best W. That's fixed, and that's fixed for each of these points in there. And W is what we're going to learn to fix, right? So then the loss function, make sure y'all can read that, it's the loss function. And I didn't mention this last time, but I probably should. This loss function that I showed you is called the mean squared error function. That's the name of it. So the loss function for a given W is equal to 1/2. Also 1/2 times n. The n, remember, is like averaging it out. Or actually, I'll put the 2 inside the sum. 1/2 of the sum from your first data point to your last data point of 1/2 times your predicted y minus the actual y. So I can introduce this subscript here. That's your ith prediction for your ith data point. There's an I right there, and there's an I right there, all squared. Can y'all read that? Might need to make your screen big for it. Now, just to recall from last time, if we're predicting this, right? So if we like pick, so for example, let's make it very, very clear. I'll call this point right here like 1, 2, 3, 4. So this would be like x5, comma, y5. That's one of the data points that we know. So that point corresponds to, here's x5, and here is y5. Right? So we know those numbers. For this x, so this last time, what was it? Age, we had that height, right? So the actual height is there, but for this red line that we drew here, this would be our prediction for that feature. Does that make sense? Because that's like, so this is like our y hat, right? So for that feature, we predict that, but it's actually that. So how far away are those y values, right? What's the distance between them? Well, it's like our prediction minus the actual value all squared. That's one way of measuring distance. So so that distance is being accounted for in the sum. What about for the first one? Here's x1. And then right there, that would be y1. And then our prediction would be like right there. So it'd be y1 hat. So how far is that distance? So if these are always really far apart, right? Then this sum is going to be big. Like, for example, like if this was our line, then notice like this, the y values for this are always really far away from the y values of all these. So that would, if our slope here, I'll call this like W1. And then this line will be like y hat equals to W2 times plus B. That weight would make this bigger than that weight. Do y'all see that? So the goal is to find the best W here. Okay. So how can we do that? Well, this is just a function of one variable, right? And we know that local minimum, we want to minimize this, right? We want to minimize the loss. The lower this is, the closer our line slope is to fitting the points. The bigger it is, the higher away it is, right? So we want to minimize this. Which means we need to find local minimum. It's a function of one variable, and we want to minimize it, and we know that we can do this using gradient descent. We learned about that last time. So in order to do that, let's find the derivative, which happens to be, so L prime of W is equal to 1 over n. Oh, by the way, the 1 over n is taking the average error, right? You're averaging out all the errors, so we're minimizing the average error for our line. So the derivative, we worked out how to do this last time, for those n points, is just going to be, well, actually we need to be a little bit careful because now our y hat looks a little bit different. So let's just like make sure that the derivative still holds up. So I'm going to rewrite this loss as follows. So the loss is going to be the same as saying so y hat is really our weight times x plus b. So this is that. It's the same thing. And then we subtract off the actual label. It's the same thing, right? Do y'all agree? That's our prediction. That's just notation that we use so we don't have to write that out all the time. So this is a sum of these pieces. So the sum of pieces, if you take the derivative, it's the, so the derivative of the sum is the sum of derivatives, right? So L prime of W is equal to 1 over N. So what's the derivative of this piece with respect to W, right? That's the variable. So if we take the derivative of each piece with respect to W, what's the derivative of the outside? 2 times a half, and then this, right? Times, what's the derivative of the inside with respect to W? It's the coefficient of W, right? So this would be times xi. So this is the derivative. Do y'all agree? Would you like me to do like a specific example with just like maybe where you're only summing over 2 things? Would you like that? Or do you understand that if you take the derivative of all of this, it's the sum of the derivatives, and you just have to look at each piece and take the derivative with respect to W. Is that yay or nay? Are we good?
I think a specific example would be helpful.
Okay. So suppose the data looks like this. I'll say like 3 and 4 and maybe 4 and 6. So that's like our data, right? So here, n is equal to 2, x1 comma y1 is equal to 3 comma 4, and x2 comma y2 is equal to 4 comma 6. Good? So we just have 2 data points. So our loss function, and let's go ahead and we're going to fix b at like 3. Again, we're not treating b as a variable. We're just going to pick it the best we can, right? So this is now this, oh, sorry. So n is now 2, right? So 2 there, 2 there. And then we have n, right? And then we have w, yeah, w times xi plus b Well, B is now 3, right? Minus y squared. So that's the loss function. Okay. And again, we don't know what W is. That's the variable. That's the thing that changes. Right? So if I write this out completely, this is going to be 1/2 times W. So what is x1? It's 3. And then B is 3. And then what's y1 is 4. All squared. And then W times what's x2 now? Times 4 plus B minus the y. Does that make sense? I'm just indexing from 1 to 2 in this case. So what does this become? Well, actually, I think plugging in the numeric values might help you understanding how to like index, but it might be easier to just do the derivative with variables, because like these are like making new numbers. So that's what that sum is for that example. But let's go back and look at, let's just think of that right there as B for now. We don't, like it's 3, but let's just think of it as some constant to find the derivative. So then, just because it looks a little bit nicer, yeah, I'll go ahead and write it down. So that's the same thing as that, right? If you just have 2 points. So real fast, like as a side note, what's the derivative with respect to W of 1/2 W times x1 plus B minus y1 squared? What's the only variable in there? The only W is inside, right? So again, if you, this will be, take the derivative of the outside, so 2 times 1/2, so we have 1/2 times 2 times the inside. And then what's the derivative of the inside of the square? It's just the derivative of x1 and W, right? Which is just x1. Right? It's the chain rule. Derivative of the outside times the derivative of the inside. And your variable is W. That's your only variable. Okay? Does that kind of clear that up?
So x1 is like a constant in this case, right? That's why
Yeah.
we bring it to the outside.
Yeah, you're treating the x's like numbers, because yeah, it is a number, right? You
Yeah.
saw it earlier when I plugged it in, it just became some number.
Uh-huh. Okay, that makes sense.
Like, if I were to write it out with those numbers, I just want to know what the derivative of this is. So x1 times w is 3 times w. Plus, and b is 3. And y1 is 4. So this is the same thing as taking the derivative with respect to w of 1/2. So then it'll be 3 times w, and then 3 minus 4 minus 1, all squared. So what's the derivative of that with respect to w? Well, it's 1/2 times, 2 times 1/2 times that, plus the derivative of the inside, which is just 3. Right? And if you look at this formula here, this is the derivative. What's multiplying it on the outside? Just the coefficient of w. So the x's and the y's are numbers, right? The w is the thing. This is the important thing that we need to figure out, the w. Okay? Okay, so we're about ready to, there's one more thing to remember. So this, you should have this written down, maybe like, I'll write it right here actually. Real nice and big so you can see it behind you when I start programming there. So just write these down on something to have next to you. The loss for a given w is 1 over n times the sum from I is equal to 1 to n of 1/2 of w times xi plus b minus yi all squared. That's the mean squared error, the loss function that we're choosing. The derivative is equal to 1 over n times the sum from I is equal to 1 to n of w times xi plus b minus yi times the coefficient of w. And then finally, from last class, we're going to use gradient descent to find the best w, to find where this derivative is equal to 0. That's the whole point, right? Or as close to 0 as we can. So then gradient descent says that we're going to take w initially to be some guess. That's our variable, right? So that function, that's our variable. And then w n plus 1, our new guess for the slope, is going to be our old guess for the slope minus some step length times the loss function evaluated at our old. That's gradient descent. And then here, alpha 0 less than alpha less than 1. The step length is in that interval. So far, so good. That's from last time. That's gradient descent. We did that one by hand, actually.
So we want to set L of W equal to 0? Or the derivative of that equal to 0?
Derivative, right? We want to find out when the derivative is equal to 0 because that means it's a critical point. In local min and local max occur at critical points. But one way to do that, to find out when the derivative is equal to 0, is to, so we know that local min and local max occur whenever the derivative is equal to 0 or the derivative doesn't exist, right? And as we discussed last time, one way to do that is to make a guess and then go downhill. The derivative tells us whether or not to go up or down, right? So since we're subtracting the derivative, we're always either moving to the left or the right in the right direction so that we're going down the function always. And I even had like a diagram in the last lecture to like always show that it's the right direction to go. Right? And again, maybe just to like refresh your memory. So if this is like your W, and that's your loss, right? And you make a guess. There. And you evaluate the derivative at that point. The slope of the tangent line is positive, right? So the tangent line of the point is positive, which means that we need to go that way. So we'd say weight 1 is equal to weight 0 minus alpha times the derivative at that. So that's positive, that's negative. So we're going to subtract off from our guess and move this way. Maybe we guess right here, weight 1. But then our tangent line would say this. So now the slope of the tangent line is negative. So if we do y2 is equal to y1 minus alpha times L prime there. So minus and negative means we're adding to W1. So we're going that way. Maybe we're right there. And the slope of the tangent line is like that. And we can do this until eventually we get like is sufficiently small, like close to 0. Because now that's like getting close to where the derivative is equal to 0, and then we found the optimal guess. Does that make sense? That's the whole point behind gradient descent. We're always going downhill at each choice of W or X or whatever variable that you're trying to minimize.
So does that mean your loss function is always going to be like a parabola?
Not always, but in this case, look what it is. The variable's W being squared. So it is some parabola. So the mean squared error loss function, there's many different loss functions you can choose. This one is nice because it's a parabola and we're going to eventually bottom out and find the bottom. There is going to be a minimum somewhere. Just look at a picture of a parabola. They always have minimums. And one reason for that is, I'll briefly digress and say that parabolas are what are known as convex functions. Convex means that if you pick any 2 points on the function, there's a line that you can draw between them that's completely contained above the function. It's like they're bowl-like. And when they look like that, you can find the minimum, if that makes sense. We good? Okay. So I need to move over to my desk now. Okay, give me a second to set up. I don't know what happened. One sec. All right. Okay, sorry about that. Share my screen now. All right, here's my screen. So I'm going to click on the Anaconda Navigator. It'll pop up something that looks like this. And then I'm going to launch a Jupyter notebook. Okay. And when it launches, it will look like this. And these are all the folders or directories on my computer. I'm just gonna go to documents, maybe UHD teaching. I don't know. I'll just make a new file inside my, no. Yeah, I'll just make a new file here in this folder here. So I'm gonna go over here and click new, and then Python 3. Now, I know all of you are very new to programming, so please let me know if you're working along with me, if you're having any problems. So go ahead and speak up if you can get, like, can you make it to this point? I'll give you a few moments. Back in the, okay, so it seems that everyone's set up now. So we're now going to import the modules that we'll need. So import numpy as np, and then also import matplot library, so matplotlib, okay, dot pyplot as plt. So that's a plotting module. NumPy is a numerical module for Python. So now I'm going to go ahead and define the data that we're going to use, and we're going to do this by hand. So when I do the pound sign here, this is just text for me to read later. So next Find some data or something. Which is text me to look at later. So the data that we're going to model is actually close-ish to a real-world data set. Okay. And this data looks like this. So we're going to say that our X data is going to be equal to 1, comma 5, comma 8, comma 10, comma 15, comma 20. Okay. And we'll say that our Y data is going to be 45,000, 60,000, 85,000, 90,000, 95,000, and then finally 105,000. So I'll go ahead and put in some text here. So X is the collection of features. And maybe Y is the collection of real valued labels. All right, give y'all a moment to type that in. Oh, by the way, you might be wondering how I ran the cell. Press Shift Enter. I didn't say that. You can either click play or type in the cell, make sure it says code, and then just press Shift Enter, and then it runs. So I'll give y'all a moment to get that. And you can just type in the chat whenever you finish up writing this down or typing this up. Okay. So now we're going to go ahead and take a look at what our data looks like using the PLT module here. So go ahead and type plt.scatter and then put X, comma, Y. Don't run the cell yet, just type that, plt.scatter. So this is the scatter method that we imported with PLT. And then we're going to give our plot some labels. So plt.x label, we're going to say that that is experience. And this will be in years. So I'm just putting a string in there to give it a label. And I'm going to do the same thing for the y-axis. plt.y label, salary, and we'll say that this is in US currency. And then I'll give it a title, plt.title. I'll just call this maybe data science experience versus salary or something. And then press Shift Enter. And I don't like that color, so I'm going to change the color inside the scatter method. I'm going to say color equals red. And then press Shift Enter again, and there it goes. Okay. Go ahead in the chat, let me know if you're able to get a plot that looks like that. All right, so this is actually not too far off from a data set that I saw recently. It's not exact, but it's close to real world data. So these are like Oh, the data that I was looking at was average salary. So I went ahead and changed the Y label. All right, so far so good. So next, what I'm gonna do is I'm gonna define my loss function. And I'm gonna define this as a function so I can call it over and over again. So to define functions in Python, you type def to get it started. And I'll call it maybe loss. And when we evaluate the loss, we actually pass in a bunch of different things. We pass in our features, our labels, our weights, and we're gonna guess a bias. So I played around with the data earlier, and go ahead and just define B, just define it to be 40,000. That's the bias that we'll use. It's probably not the best bias, but that's the one that we're going to use. And we're going to fit the slope. Okay. So be sure to have that bias down. So now we're going to define the loss. So the loss, we're going to take in weights, or slope. Yeah, I'll say slope. It might be more descriptive. Slope. And then our intercept, which is the B that we plug in. I'm just trying to be as descriptive as I can with the names I put into this. And then features and labels. Oh, not in, sorry. Labels. Now to enter into the function, now press colon. So notice the white space here. That means that we're inside this function. So I was using in to denote the number of features and labels, right? The number of points, right? So I'm going to go ahead and say that n is equal to the length of features. I'm assuming that features and labels are the same length. Right? Okay, so that defines my n. And then we need to look at that. Did everyone write down that equation earlier? The loss equation, what it looks like, it's a sum, right? So Python is really easy, is really natural because it's readable. So hopefully this makes sense. I'm going to say sum differences equals the sum, right, of all. So slope times feature or features I. Remember, X is always the features, right? So features I plus intercept minus labels I. All squared. And to square, you do 2 stars and a 2. For I in range n. So I'll break down this, what this means in a second. Be very careful with all of your parentheses. Even make it bigger so you can read it. All right, now, so here, just to be clear what this is doing, we're summing slope times x plus intercept minus y, all squared, for each I from 0 to n minus 1. Like this basically takes, this is indexing through all the data. That's what this is doing. There's n things there, and we're just looking at we're counting from the bottom to n, -1. Does that somewhat make sense? And then we're going to return in this function the sum differences divided by 2 times n. Now we're out of the function. Does this look like sort of look like the function that you had written down? It's the sum of all of these things for each of the data points. Does it look the same? Let's go ahead and like test it out real fast to make sure it works. It's good practice so I'm going to press Shift Enter to run that cell. So let's just test it out. What is the loss? And let's take the slope to be, I don't know, what's a good guess for, I'll say like this, the slope is like 1,000, just like looking at it, maybe it's 1,000, I don't know. And then we already have our intercept, we call it B up here, so I'll say B. And then our features are X, and our labels are inside of Y. Let's see if this runs. There's our loss. It's really big. So let me know if your function is not returning the correct thing. Well, it might like make a different number than this by a little bit, but does it run? Is it giving you some number?
So back to where we defined some differences, did we create a for loop, or is that part of the functionality of the sum function?
It is a for loop, but it's called list comprehension.
Okay.
For each I in there, you're doing that and you're summing all of them. It's very common practice in data science. Very common. What are you doing? You're summing. Summing what? This. Where does that come from for each I there? Okay, so I tested my loss function. I think that it's working. So now I'm going to define the derivative because we're going to need the derivative for gradient descent. So I'll say def loss derivative, trying to be descriptive. And this is going to take the same stuff that loss did. So slope, intercept, features, and labels. Colon, go inside the function. So as before, I'm going to get my n first. So n is equal to length of features. LEN is just the length or number of things inside there, which is the number of data points that we're looking at. And then if you look at the definition of the derivative, we also have this big sum thing, right? So we can do sum differences again. Sum, what are we summing? It's basically this, right? That's so just put that like right there. Times the coefficient of that slope variable. So features I. For I in range 10. So hopefully this looks just like the derivative formula that I wrote on the board. And then we're going to return some differences divided by n this time because the 2's all went away as we found out on the board. There's my loss, and then maybe I'll do loss derivative, put put in, suppose our slope is 1,000 again. Put in b, put in x, put in y. All right, so we have some derivatives. Okay. Now, in fact, we can go ahead and we can just do this. Like, so go ahead and type exactly what I typed here. So I'm going to say W0, our initial guess. I'm going to guess that to be 1,000. Okay. And then I'm going to make a domain that I'll need for plotting. I'll call it domain. And you don't need to really understand what this part is, but I'll tell you anyhow. Nope, 1R. So all this is doing is calling that numpy thing, numpy thing from above, and it's making an interval from 0 to 20 with steps of 0.5 in between them. It's just, it makes plotting easier to make you need a domain to plot functions, basically. And then I'm gonna do plt.scatter, put in your x and your y, and let's color those points red. And then I'm gonna do a plt.plot. Now we're gonna plot our function. Actually, go up to the cell above it and click on it. And then see this little plus thing right here? So I'm in this cell right here. I'm gonna do the plus and I put a cell right there. I'm gonna define our function, the line that we're trying to get. So def our line. And our line takes a slope and an intercept. And all this, slope and intercept and an x. Like that's a little x. This just returns slope times x plus intercept. You just run that cell by pressing Shift Enter. So this is a way that we can just, this is the line that we're looking for. The slope is what we're going to try to find. And
Sorry, how do you create that cell again?
oh, I just went above and I clicked right there and I hit the plus button.
Okay, cool.
And it just puts a cell underneath it. So this will be useful to plot our line that we're trying to find it, just to see what it looks like. So now we're going to plot the line. So we give it the domain we made. And then we give it the function line. Oh, didn't mean to do that. I'm going to put line right there. And for our slope, we're going to put W0. For our intercept, we're going to put that b that we defined above. And for x, we can just throw in the whole domain and it'll plot it. Okay. And I'll go ahead and give this like color equals, I don't know, green or something. Okay. And I'm going to go up here and I'm just going to copy paste this. Copy, paste. So I don't have to type it again. So with each of these lines, you're just making your plot look nice, basically. That's what you're doing to it. If you just wanted to look at the line in your data, you would just plot that. But you like your plots to look nice, so give them some labels. All right, so I'm just and this will all make sense later. I'm just like, we need to get this one cell, and then we're just going to copy paste, copy paste, copy paste, copy paste after we get this one cell going. So this right here is just, we're taking our wild guess at our slope, and we're putting it into our loss, and we're seeing what that is, and it's going to print it out. So everyone have all this stuff? All right, so let's press Shift Enter. There. Does everyone see a plot that looks similar to this? Actually, I'm going to make my domain a little bit bigger. I want my line to go further. So I'm going to go up here to np.arrange, and I'm going to make the right part, I'll make it 25. And then I'll run the cell again. So the line goes a little bit further. Okay. So now, are we all good? Can I move to the next cell? I'm going to copy paste all of this, and we're going to be using it over and over again. All right. So just copy paste this. So copy, paste. So now I'm going to say that W1 is equal to W0 minus, and I'm going to choose alpha to be some number between 0 and 1. I'll make it like 0.005 or something. Times, and then up here we have the loss derivative, right? Loss derivative, and we put in there W0, and then our bias, X and Y, our intercept, I mean. So this is gradient descent. This is one step of gradient descent. You see that, right? New W is equal to our old W minus alpha times the derivative at our old W. So after I do that, I'm going to go over here. I'm going to copy that, go right underneath it, paste, and then instead of 0, I'm going to do 1, and then right here, I'm going to do a 1. And then if I run this,
Do you have to change W0 to W1 in your plot?
oh, yeah. Yeah. Oh, what am I? Yeah, good call. Go here, copy that, paste, and then put a W1 right there, and color it something else, like blue or something. That's pretty cool. We just did one iteration of gradient descent, and look at how better our blue line is than our green line. Do y'all see that? More importantly, do you have it running on your computer? So what do you think we're going to do next? Copy. Now, if I was doing this for a of course, where the students had a lot of experience in programming, I would write a loop to just do this over and over again. But we're doing it by hand right now. So replace that 1 with a 2, replace that 0 with a 1, replace that 0 with a 1, copy this, paste it, replace that 1 with a 2, that 1 with a 2, and then let's make sure we include our this will be W2, and we'll color it, I don't know, orange or something. So we update our, so W2 is equal to W1 minus alpha times the derivative of W1. That's gradient, that's one step of gradient descent. And then we're gonna print our loss so we can like look at our loss compared to the other ones. It's getting better. I'm actually curious though. I'm gonna copy this real fast. And then in the here, I'm just gonna replace this by derivative. And then derivative. And then this is the loss derivative. Loss derivative. Loss derivative. And then press Shift Enter. Yeah, see, the derivative is, the value's hopefully getting close to 0. So let's go ahead and run this again. I'm gonna take this, copy it, paste, and as before, just do the same thing. Replace all the indices. So this W3 is gonna be W3, W2, W2, copy, paste, W3, W3. We're gonna run out of colors. Maybe red. And this better be a W3. Make sure I did everything right. Press Shift Enter. By the way, it doesn't look like the numbers are changing, but if you think about it, they're changing a lot. Like, what is that? So, the loss decreased by what, like 400,000? I wonder what our derivative is now. So I go back up here, I copy that, and I paste, and then I can just look at the iteration 3 by just copy and pasting and putting a 3. Yep, it's getting smaller. And the whole goal is to get close to our derivative being 0, right? I guess I'll do it one more time. You don't have to do it one more time, but I'm gonna do it one more time just because I'm curious. Must be a 3, 3. What color should I use? Black. I'll use black. I'll just copy that. Okay. And this is such bad practice to do this, but I don't want to go into like for loops and the intricacies of that right now because this isn't a programming course. I'm just using Python to illustrate an idea. Our derivative's getting smaller. Okay, I'm just curious. One last go. I apologize. I'm just going to increase my step size. Look how small my step size is. I'm going to increase it and see what happens. There. Let's see what happens. I don't know. And then I'll change this to 5, 4, 4. Wow, I haven't done this in a long time. I haven't programmed like this in a long time, but it's, I guess, the only way I can do it for y'all. I think I might have shot up too much. See how it shot up? It looks like my loss increased too much. So maybe I took too big of a step size. And remember how we were talking about how much we step left or right is important. So maybe that was like way too big. Maybe if I do that. Still seem too big. Okay, we got some decrease there. So this is playing around with this, what's called a hyperparameter. It's something that we play around with to make the model learn better. So real fast, I'm just like, I want to know what my derivative's value is right now. Yeah, it did get smaller. Okay. So that will be, well, like, okay, you can just imagine though, like, here, I'll just go ahead and show you. And you don't have to program this at all. What was my W to begin with? It was 1,000. So just, I'm gonna go really fast for a moment. You don't have to do this. Say, slope, intercepts, features, labels, max, I'll call it alpha. And again, you don't have to do this. I just want to show you what the idea is. Yeah, I'll just put it in there. Technically need to give it a derivative. So I'll just yeah. I'm going really fast right now, so I apologize. This is just, I want to show you this before we get off the Zoom meeting. I already have this function. Why am I doing this? I already have it. I don't know why I'm doing this. I'll just call it, that's what I called it, right? Where is that function? Mine. Yeah, okay. Okay. Where's the problem? Oh, why does it do that? These are like things that I defined to be there by default, right? All right, so basically then I would say uh, my slope equals to gradient descent. Take a random guess at what the slope is. I don't know, 15,000 or something. The intercept we'll choose to be B. Let's throw in X. Let's throw in Y. Let's throw in the function loss derivative. And then there it goes. And then oh yeah. And then let's say that we have 12 years experience. We should expect roughly 85-ish thousand dollars. And if you look at 12 years experience and we look around 85, so plus or minus, our line is right about there, which is roughly in relation to all these others. So for example, if I look at like 5 years experience, 58,000 roughly, and what was our actual data up here? Where is it? There. 5 years, 60,000 is what it was. And we just predict 58. So it's like plus or minus some thousands of dollars. But what did we just do? Notice that we just took a random guess at the weights, the slope. And then we used gradient descent, which is using the derivative to always go down, right, downhill, until we did that about 10,000 times. And what did gradient descent do? It learned on its own, without us knowing, it learned what the slope was. And once it learned that, then we can make predictions about salaries based on experience. Now, there's some caveats about linear regression that I'm not touching on because that's not in the scope of this class, but that's the idea behind machine learning. Let's make another guess. Like, what if we guessed like a slope of, I don't know, suppose we guessed 10. It still basically did the same thing. Our guess was so terrible. Let's guess something awful. Like, what if we guessed a slope of 0.05? It still learns, right? And then we can also vary the intercept, right? We kind of chose that randomly, but different intercepts are going to give you different lines, right? Okay. So I'm going to end the recording there.